we need some terms to describe, besides saturated and unsaturated. We deal a lot with unsaturated solutions, and there's a big range there of how much solute is dissolved. So we have two words that we used qualitatively, and that's dilute and concentrated. And those mean the same thing that they do in everyday life, right? What's different about concentrated orange juice as opposed to just orange juice? Can you just thaw out a can of concentrated orange juice and drink it? You could, but ugh. What do you need to do? You need to add more water, right? Because they took some of the water out. The water's the solvent. It's more concentrated. It's got more orange goodness in it in a certain volume than in just like fresh squeezed orange juice. So dilute has a small amount of dissolved solute. A concentrated solution has a large amount. They are qualitative. There's no numbers involved. It's very relative. Of course, chemists aren't really into a lot of qualitative stuff. We like numbers and measure it, right? So one way to measure the concentration is to use a percentage. So a mass percentage compares the mass of solute to the mass of the solution. So a mass percent is mass of solute divided by mass of solution. I've told you before that the percentage is the part over the whole times 100, right? So the part over the whole. The whole thing is the mass of the whole solution. The part is the solute that's dissolved. You've got a sodium chloride solution. Maybe it's 0.9%. That means you've got 0.9 grams for every 100 grams of water. Water of solution. The very easy mistake to make is to just use the solvent in the denominator. And we'll have a couple of examples. They'll give you the mass of, say, the sodium chloride and the mass of the water, but you need the mass of the whole solution, so you need to add those two in the denominator because you need to get the whole thing. My oldest son, when he went to kindergarten, there were 15 boys and 5 girls. So what percentage of the children were male? 15 boys, 5 girls. How many children in the class? 20. So 15 divided by 20, 75%. But what the mistake that you make if you don't add those two together is you say 15 boys divided by 5 girls times 100. Oh, 300% of the children were boys. No, that doesn't work out very well, right? It's boys plus girls. So it's 20, 15 out of 20. So you have to divide by the whole thing. So let's do an example. What is the mass percent concentration for a solution containing 5.57 grams of strontium chloride in 225 grams of water? Well, which of these is the solute? The SrCl2. The solute is the thing that's dissolved. The thing is smaller amount. So it's the 5.57 grams of strontium chloride. What's the solvent? The water. 225 grams of water. We want, for our denominator, the mass of the solution. So the mass of the solution equals these things added together, right, which would be 230.57 grams. Did I do that right? Sometimes I do math like that because I don't want to get out my calculator. Oh, I did it right that time. Good. So the mass percent then, oh, I should probably write it the way they do it. Mass percent equals the grams of solute divided by the grams of solution times 100%. So I've got 5.57 grams divided by 230.57 grams times 100%. The grams cancel out. 5.57 divided by 230.57 times 100. That'll have two significant figures, 2.42%. Is that a reasonable number? Yeah, it is. The mass of the solute is much smaller than the mass of the solvent. And so it's going to be much less than 50%. If you come up with a percent concentration that's over 100, you did something wrong, right? Because the whole always weighs more than the part, right? Because you're adding two things together. It just can never be. The percent concentration is always less than 100%. Any questions about that one? Mass percent can be used as a unit factor to allow us to calculate how much of a solution we need to get a certain amount of solvent or solute or whatever we're needing. So we need to remember that percent means parts per 100. So 25% sodium hydroxide means 25 parts of sodium hydroxide per 100 parts. Well, what is a part? You can pick your unit. This is a mass percent, so we need to use mass units. But you can use any mass unit as long as you use the same one on the top as you do on the bottom. So we could use grams. 25 grams of sodium hydroxide per 100 grams of solution. So this is per grams of solution. Or we could use kilograms. 25 kilograms per 100 kilograms of solution. The units cancel out. As long as they're the same, we're fine. So that's one unit factor. That relates sodium hydroxide to the solution. We could also turn that upside down, right? 100 grams of solution per 25 grams of sodium chloride. Because for this solution, those two things are equal. How would we relate the mass of water to the mass of solution? If it's 25% sodium hydroxide, what's the other 75%? Pardon me? Water. This solution only has two components. You can have multiple components in a solution, but this one has two things, water and sodium hydroxide. So that means if it's 25% sodium hydroxide, it must be 75% water. So then we could write 75.0 grams of water per 100 grams of solution. Does that make sense? Because the two parts have to add up to 100%. 75 grams of water to 100 grams of solution. What's the ratio of grams of water to grams of sodium hydroxide? Oh, I see what he was saying. Yeah, I goofed there, didn't I? And I kind of heard you, but I didn't fully hear you. Yeah, it's not sodium chloride, it's sodium hydroxide. Well, there's different ways to think about this. What if we took this one and multiplied it by this other one? What if we took those and multiplied them? These would cancel, right? And we get 75 grams of water per 25 grams of sodium hydroxide. I left the unit out. You don't have to do that one as often. Being able to do this one, I'll put a box around it, relating the mass of solvent to the mass of solution, or the solution to the solute. Those are the most common ones. It's important to remember percent means parts per 100. Okay, any questions? I don't think that went very well, but it's too late now. You might want to watch last semester's video. I think it was better. Calculating mass percent concentration. So there's two basic types of mass percent problems. One is they're asking you to find the concentration. We already did one of these. You need to figure out the mass of your solute and the mass of your solution. If they give you the mass of solvent, you need to add the solute and the solvent together to make up the solution. Those three words get really confusing, don't they? And then you just use this equation. So we did one of those. The other type of problem is where we're looking for the mass of the solute, the solvent, or the solution, and they give you the percent concentration. Then what we're going to do is we're going to use the percent concentration as a unit factor and do unit analysis to figure out the quantity that we need. And these are the sorts of problems that you could encounter in a hospital lab, or a nurse might even need to do something like this. So we have a 7.5% potassium chloride solution is prepared by dissolving enough of the salt to give 100 grams of solution. What is the mass of water that is needed? So we read through the problem, and here we have a number. So let's write that down and identify what that means. 7.50% potassium chloride. What does percent mean? Parts per 100 parts. Here we're using the unit gram, so let's just use grams. That means 7.50 grams of potassium chloride per 100 grams of solution. And then we've got this quantity here. We've got 100 grams. Oh, I left off a decimal point and a zero. 100.0 grams of solution. And what do they want us to find? Mass of water. Mass of KCl is easier, isn't it? We already have the unit factor right there. So there's two ways you could approach this. The mass of the solution is 100 grams. So we could calculate the mass of potassium chloride, and then the difference between them would be the mass of the water. Or we could calculate the percent water and find the mass of water that way. Which one would you like to do? The second one? Okay, so to find the percent water, the solution is 100%, right? And so we subtract the 7.50%, and we get what, 92.50% water. 7.5% of it is potassium chloride. The other part of it must be water. So that means 92.50 grams of water per 100 grams of solution. That's how chemists abbreviate solution. We get tired. Now we have what we need. 100 grams of solution. And we're just going to look at the units. I want grams of water, and I want to divide by grams of solution. So I'm going to put the units in. Well, that's that one too. So they cancel out. And then I look at this. It's 92.5 grams of water per 100 grams of solution. So you could look at that and say, oh, the hundreds cancel out. That's just 92.5. Or you can do it on your calculator, and you'll come up with the same answer. 100 times 92.5 divided by 100, 92.5 grams. Any questions? A lot of solutions in medicine are percent solutions because they're easy to make up. So you take, you need a certain amount of a solution, or you have a certain amount of solid, and all you need is a balance. You can make this up in a beaker. You don't need to measure volumes carefully. You just need masses. So it works out to be a very easy thing to do in the lab. Let's do another one. What mass of potassium carbonate is dissolved in 10 grams of 2.5% K2CO3 solution? So that is potassium carbonate, right? Well, we've got two numbers here. We've got 10 grams, and we've got 2.50%. This is 10 grams of potassium carbonate, or water, or what? Grams of blah, 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 solution, right? Sometimes, and I do this, you read a problem and you see what you want to see, right? You don't actually see what's really written there. And then you do this great solution and you did all your math right, but you answered the wrong question. That's always tragic when that happens on an exam. 10.0 grams of solution. And when we see percent, we should say, oh, that might be a unit factor. 2.50% means 2.50 grams of the solute K2CO3 per 100 grams of solution. Pardon me? We have 10 grams of the solution, but this is 2.5 to 100. They're kind of boring with their numbers. They're using 10, 100 a lot. It's like, well, what's wrong with 7.593? That'd be more interesting. So here we have our two quantities, and we're trying to find mass of potassium carbonate. We have two numbers here. This is just grams, and this is grams per 100 grams. This is a unit factor. Let's start with this one and see if we can get to the other one, what we're asked for. So 10 grams of solution times something. We want grams of K2CO3 on top, and so we'll put grams of solution on the bottom. So those units cancel out. This is the relationship given by the percent. 100 grams of solution, 2.50 grams of potassium carbonate. So that comes out to be 0.250 grams of K2CO3. Any questions? What I'm showing you is not the only way to solve these problems. Some of you may have become proficient with using percentages in a business class or in high school or something. And if you're a whiz with percentages, just go ahead and use them, that's fine. But if percentages give you a little trouble, this way will work, okay? So down here we have a picture of 5% dextrose solution. This is the sort of thing they might hang on an IV and give you intravenously if you're in the hospital. A 5% dextrose. Dextrose is the same thing as glucose, essentially. And so a question is, what mass of that solution will contain 5.36 grams of glucose? They want to know, how much of the solution should we give this patient? We don't want to give them all of it because maybe that would be too much sugar. Well, again, we have a percent and we have a number with just a plain old unit. So this is what we're going to start with, and we're going to use the percent as a conversion factor. So 5.36 grams of glucose, or dextrose, it's just another name. And what are we trying to find? Mass of the whole solution, right? So we're looking for grams of the solution. We want to divide by grams of glucose. So I get my units in there. Then I've got this 5%. So 5% means 5 grams of glucose per 100 grams of solution. So I need to keep 100 grams with solution. And we can't switch it up and say there's 100 grams of glucose in 5 grams of solution. It's not possible. This is 100 grams of solution, 5 grams of glucose. So 5.36 times 100 divided by, yeah, that wasn't the divide by button, 5.57 times 100 divided by 5. 111, I'll write it down here, 111.4 is what my calculator tells me. How many significant figures should that number have? Well, this one has 3, and 3 is a nice guess, but what about this 5%? That seems super fancy official and must be an exact number, right? No, that has one significant figure. Getting 107.2. Oh, yeah, because I'm taking 5.57. Where did I get that? Thank you. Yes. Just seeing if you're on your toes. I'm just making things up as I go along. Good grief. Shoot me now. Yeah, 107.2. 107.2. So if we were to round that to one significant figure, what would it be? Well, we could write it in scientific notation, right? If we put this into scientific notation, it's 1.072 times 10 to the 2. So we say 1 times 10 to the 2 grams, or 100 grams. And that seems, that bothers some people. But the calculation said 107.2. We have to use exactly 107.2. But if this 5% only has one significant figure, that means it's between 4 and 6%, then this little 7 grams here doesn't really matter. And so we're going for 100 grams. I know it's disturbing. Any questions?